Greetings, travelers. Today we're going to go over airflow. This is my home mining room. There's the exhaust over here behind this louver to minimize water infiltration. And on the other side of this building, there's two of these as an intake. So the air gets pulled in from that side and pushed out over here. You can see my neighbor has a back patio area over there. So I'll talk about the hows and the whys. I have my system designed like this, and maybe it'll help you design your system or get some ideas. So starting off, there's my exhaust fan array. We'll go over that in a bit. We'll just get a feel for the layout here. And I got all the rigs moved up now. There are 3 8-way 3070 rigs and a miscellaneous rig with 3080, 6800 XT, 5700, various things. You get an idea of the temps that the 3070s are running at. These run quite cool. You can see the fans only at 60%. Temps are fine. Memory temps are barely higher than that. 91 degrees Fahrenheit here, 88 over there. And we'll look at the A2000s. Little cooler over here, and that is the temperatures that those guys are running at. A few restarts on this rig still. This is the only one that has thermal pads on it though, so that's the best indicator of what those run like when you have pads changed as well. And here's my intakes. There's 2 of these. These are a little dirty right now. And the temperature sensor for the intake is stuffed into the screen over there. I'll get this framed out, and I need to make a sound baffle that will stick out and force the air to maze around foam before it comes in from here to minimize the noise that leaks out. So anyways, my fan array. It's a little unusual, you may have noticed. These are server fans, 3 amp, 12 volts, and they have PWM, of course, so they're speed controllable. And what I like about this rig, well, one of the reasons I like it is how close it fits into the window, how low profile it is. With trim around here, it actually be slightly countersunk, and the power density is quite high. There's pros and cons to this, but I'll show you the benchmarking data, and you can judge for yourself whether or not this actually is effective. A few people had some questions and concerns raised in my previous video, which I do appreciate all the comments and support. It's awesome. But we'll try to go over why I have it like this and why I think this is a decent and viable approach. Here's my temperature controller. So you can see right now the fan speed is 5, and I have, these are the over, minimum, under temperature speeds. It'll go from 0 to 5 if the temperature is out of these ranges. You can see right now it is above this 90 degrees high T set. And this is the normal speed when it's operating as a differential cooler. But you can see, although the differential is programmed at 12 and it's operating at 9.5, it is a green box, it's satisfied. That's because it's out of bounds. The indoor temperature is above the high T set, so it allowed it to increment to try to push the temperatures down. A few reasons for this. Go over the graph. You can see this is the outdoor temperature and this is the indoor temperature in yellow. If you look at the number of spaces between here compared to here, this isn't the best example because it's only 92 degrees in here right now. Yesterday it was quite hotter and it worked a little better, but it kind of compresses the space. It squeezes this yellow line, the indoor temperature, together by knocking down the highs. And if the lows get too low, it'll push up the lows as well. It'll minimize the temperature differentials that the cards and the silicon see. It will also ensure that the indoor temperature, and as a result, the humidity, stays under control. It doesn't directly measure indoor humidity, but it doesn't need to. And as long as it ensures there's a differential, I'll ensure that the cards don't see too low of a temperature mechanically. But I'll go over that when the weather gets a little colder. But that's kind of the point of this system. It's to compress the space the cards operate in and save power, save airflow through the building, through the filters. Because if you just had this run cranked all the time, it would be very loud, take a lot of power, and push a lot of unnecessary air for no reason. And that'll mean the filters will wear out much faster, among other factors. The fans wear out faster and all that. And I'll show you what this looks like when this fan is running at full speed. It's quite loud. So that's full speed. You can see the RPMs come up. There's the differential pressure, you know, nearly 50 pascals. These fans will do around 400 to 450 pascals, but we'll talk about that because that's a big issue. Static pressure tends to be very misunderstood. And I'll show you the data that these fans have on that. So there's 5 is where it's running, and this is the minimum fan speed. And these are controlled. There's 2 power supplies running this, and this will turn off one of these power supplies if the temperature continues to drop indoors below the setting. So it can actually turn half of these fans off to minimize airflow even further. But I'll just put it back, and we'll talk a little more about everything else. Oh boy, there we go. So you can see right now it's running at a fan speed of 4. I'll bump that back up to 5. It'll do it automatically, but it'll take a bit. And you can see the pressure. There's a hose going outside the window, and it's measuring the pressure difference from inside to out. And this is an indicator of how much work the fans are doing to move the air. Because you take a box fan, you put it in free air, although maybe the fan blades and around the fan are experiencing a pressure differential, that's its design conditions. That's what it's rated. So when it's rated 3,000, 5,000 CFM, it's rated typically with no static pressure. And that's very misleading because you never really have no static pressure. You could have fairly low static pressure, but never none. Any duct, any restriction of any kind will impede airflow. And you look here, that is the pressure in the building right now. When I open the door, and the pressure drops, right? So this is because it's easier for this assembly to jumper air out the door right into it than it is for it to get it all the way over from the other side of the room, through that screening, through the louvers, through the restrictions. And even things like this, cards in the way, will add static pressure. A lot of fans will have a graph showing you over its operating range how much pressure it could generate. These fans at 13.8 volts will do 450 pascals. That's a little misleading though, because it's also at 0 CFM. So obviously you want airflow. It's a balance between how much pressure you can make and how much airflow you need. So ideally you would estimate your static pressure drop, and if you have filters, you could drop 50 to 100 pascals just on a filter. And that could be with a clean filter. Depends on your surface area, the size, if it's pleated, how many pleats, the density of the pleats, all these factors. So right now I'm operating around 50 pascals at full speed. That pushes us right here. You can see the difference in this line. Not too much airflow reduction on these fans because of the 50 pascals. And you can see at different PWM states how that affects the pressure and the airflow. It's really quite substantial, right? Here's a little benchmarking data that I had. How I got this was I took the interior diameter, the measurements of my intakes over there. I measured it, right? And you plug in the little calculator online. I measured the air velocity with this, and assuming that the airflow is laminar, perfectly even, there's no obstructions and all that, you could estimate pretty accurately the airflow. And so here we are, 3,395 CFM. That's per intake. And coincidentally, the velocity between the two systems is actually very, very close and even all the way across. I measured it in a bunch of points and on both of them, and it was very even. So this is a decent start, but there are the slats in the screen take up a little bit of space, so it could interfere a little bit with the measurements. I just took 5% off because that's like a best guess approach. But that's how I got this data for airflow. I graphed the airflow that I see at the different speed states on my PLC, from -1 being one of the fans, one of the power supplies off and the fans at 0, all the way up to 10. And you can see it started out, where's the numbers here? Started off at 1,700 CFM and went all the way up to 6,800 CFM. And this was done 2 days ago when the filters on the intake were a little dirty. So in ideal conditions, the numbers will be higher than this, and with dirty filters, it'll be lower than this. And I plan on adding filters, so all these numbers get pushed down as a result. So I need overhead to accommodate that. And on top of that, here is the power consumption as it relates to airflow and speed. It is the airflow per watt versus the fan speed, and a higher number is better because it means more air for the same power. And you can see starting off all the way down here, how efficient it is. And then when it goes from -1 to 0, all the difference here is one fan bank is on and 2 fan banks are on, same speed. So this shows you the effects of efficiency, well, the effects of static pressure on efficiency, because these fans are running at the same efficacy here. However, there's 2 banks on and only 1, and so as a result, it takes more power to be able to pull the air through the room, because there's a little more restriction, because more air is trying to get through the same space. And you can see it falls off really severely as the speed increases. All right, so here's 5, which is what they're running at now. It's 11 CFM per watt. Not terrible. Over 20 is considered to be pretty efficient. Obviously, it depends on your system. But I should note, this is in the system, actually installed delivered air. So if you look at just numbers for a fan assembly or just a fan, they're misleading because they don't take into account your system, the actual airflow you will get delivered as a result of your static pressure. You can estimate how much airflow you need pretty easily using calculators online. And I was shooting for around a 6-degree temperature rise at full fan speed with 10 kilowatts. So these numbers are for 10 kilowatts of heat. And you can see the airflow required changes with the temperature because the amount of cooling the air could do changes with the temperature. Colder air is more dense, so you're pumping more of it as a result. And hotter air, less dense, you're pumping less ability to do temperature change, to be able to move heat with higher temperatures. So these numbers show that in a 100-degree environment, I need 4,173 CFM for an 8-degree differential, and then for 6-degree, 5,564. That's quite a lot. I need 5,500 CFM delivered, and that needs to be 100% efficient. That means effectively all the airflow that you're delivering needs to run past stuff that's producing heat. If it's just creating turbulence, it's moving around, it's moving past something that isn't making heat, it gets wasted. So these are the best case numbers. And looking at my benchmarking data, it does actually validate one another, because this is pretty close to what I see. I see around 6,800 CFM delivered at full fan speed, and I tested this with 10 kilowatts, and I got around 6.4 degree delta with clean filters. So that seems to be believable, that the estimates show 5,500 and I have 6,700, and the numbers more or less correlate. So I have about 20 or 30% worse than nominal setup, but considering it's just like cards put in front of an opening in the wall, I think that's pretty good. And what I want to do eventually is put material around here, some foam board or something, to duct the air into these rigs and get rid of these box fans. These box fans are just here to make sure that the heat gets pushed out the front and doesn't just stir around in here, because otherwise you get issues with some cards getting much hotter. These cards actually run pretty good with these optional fan things. I make these little fan shroud things for these A2000s. These run pretty good compared to stock without the box fans, but the box fans help a little bit. So for now I'll run them. And these are very problematic because of the design. The heat gets pushed out the side, the heat kind of swirls around, and you see 15, 20 degrees C, higher temperatures without the box fans. So you kind of need it for these, but I want to make a duct system that all the air that's pushing out has to get pulled in across the cards and out. And that should allow me to save around 500 watts with all these box fans being eliminated. But onto more of the hows and whys. With this system, I chose it like this because I have one intake or one window here and 2 over there. And over there is fairly close to my neighbor. So I didn't want to put fans in the window over there because it'd be louder, harder to mask the noise. Over here, there's a good amount of space to my neighbor that way. So it's really not an issue to blow that way. And on top of that, I was more worried about how long the fans we'd be able to run without service. I didn't want to have to keep changing filters. And if you only have one intake filter, trouble is you got to clean it more often and you have more static pressure drop. Typically fans get better efficiency. Well, I should say efficacy. Sort of the same thing, but people confuse the two. Fans typically get better efficacy with an exhaust restriction rather than an intake restriction. And you can see here, this is a little dirty, kind of maybe hard to tell in the video. This is a little dirty. This gets very clear when it's totally clean. There's like bugs and stuff in here too. And on top of that, I assumed it would most likely be harder to service if I had the fans over there and an intake filter behind the fans. Because ideally I didn't want to be pumping bugs and stuff like that. I have a lot of airborne insects in this area. I didn't want bees, bugs, and sort of things flying into here, which they would, or getting sucked in and going through the blades of the fans and getting spewed everywhere, or whatever would happen, or nesting in there and stuff like that bugs do. So for me, it keeps these fans fairly protected over here, and I could filter it over there with more surface area. And these fans fit pretty nice. They give you good speed control, a lot of redundancy. 2 power supplies means one could fail, and you have another, and very wide operating airflow range. This will go down to, I'll probably put the voltage down on those power supplies, and this will go down to around 1,000 CFM with the voltage turned down at a minimum speed, all the way up to 7,000 CFM, which is a pretty good range. Usually you don't see that. Usually on most fans that have a wide speed range, you throttle them through a VFD or some sort of controller like that, and it's a AC induction motor. Those can get very inefficient at low speeds, whereas they tend to get much more efficient, higher efficacy at high speeds, or at least medium speeds. These are kind of the exact opposite. So for me, the design I wanted to have overhead. These fans have a lot of overhead. They have about twice the airflow I need for this room as it sits, which is always a good thing. It'll accommodate static pressure increases as the filter gets dirty and if I add more hardware and that sort of deal. And it just basically means these fans don't need to run flat out, which, if you look at the graph, pretty big advantage there, right? You can see very efficient actually in this region. This is 36 CFM per watt delivered, and it drops all the way up to 6. So at low speeds, these are actually quite efficient. And the normal range they run at in normal temperatures, 23 CFM per watt, that's actually pretty good for delivered airflow. It'll get a little loose with filters, but overall not bad. I think this assembly is pretty good for my application. Certainly not for everybody. It's a weird, unusual, complex assembly, but I don't really see how people don't think it's a viable option. It obviously is working. Right, here we are. Fairly warm day, relatively speaking. It was 93 degrees Fahrenheit yesterday, and the highest temperature I saw was, I believe, around 97. I could actually look if I go back here. Yeah, there's the temperature peak yesterday, and if you look at the outdoor temperature for that time, oh boy. Okay, outdoor temperature for that time, okay, it's reading around 88 peak. So overall, it did pretty good yesterday. It really compressed the space. This one I can't slide, but it worked pretty well. It compressed this around 2 blocks. So it was like around 5 over here and it was around 3 over here. As the temperatures increase, this actually compresses a bit more. It's slightly non-linear. So this system seems to work pretty well. It gives you good control. It ensures that your indoor humidity is reasonable at all times, minimizes power consumption, minimizes airflow through filters. One of the big downsides is, at least in my implementation, it is exhaust only. It's depressurizing the building. However, I put extensive effort into ensuring that this building is airtight. Underneath this bottom plate here is thoroughly caulked, cleaned, inspected, the whole deal. Around the windows, I have foam and, well, I mean, it's kind of plastered over and all that stuff too. But I pressurized this room, filled it with smoke, inspected the outside, looked for leaks and repaired them. So this is actually fairly airtight, relatively speaking. So the vast majority of the makeup air will come in through there. Normally, exhaust-only ideas can be problematic because you'll get makeup air from around the windows, through leakage in the outlets, underneath the walls, gaps and cracks. And the trouble is, this is a wooden frame structure. Air brings moisture with it, and moisture can bring problems, especially if you just had the fans running flat out and it was cold outside. It would be very cold in here, and drying would not occur. The indoor humidity could be potentially quite high, and the interior walls with all the leakage and moisture pulling through it, you could get rot, mold, mildew, those sorts of deals to be avoided. So you always want to make sure that the building doesn't get too cold, unless you have a steel building or something like that that could tolerate it. And on top of that, there's really no advantage to the silicon seam like 10 degrees Fahrenheit. They don't really care that much. As long as they're a reasonably cool temperature, below that has minimal advantages. And then you can compress the space, the temperature the silicon operates in, which minimizes expansion and contraction and can help aid in long life. Either way, I think that's a decent overview of my methodology, my reasoning. I'm sure I'm missing things, but leave some comments below if you have any questions, what you think about the setup or whatever, what you want me to cover in a future video. Take care.